It's worth mentioning every so often that it's much better for the student to try to do the problem before watching it done and see how the student does before watching someone else do it. And then you can give yourself a grade and assess yourself on how well you understand the material. That should always be the case, but I just thought I'd mention it at the beginning of this example. We're going to take a look at the logistic equation P of t equals 5,000 divided by 1 plus 39e raised to the negative 0.2 t. And we're asked a number of things about this equation. First of all, the carrying capacity. Well, let's recall that the general form here is L over 1 plus B times E raised to the negative K times T. So we can kind of use that to locate some things. The carrying capacity we know to be L, so we can simply see that L is equal to 5,000. Value of K, of course, is whatever the coefficient of T is. So K is equal to 0.2. Notice that we have a negative here and we have a negative here. So K is not negative 0.2. It is simply positive 0.2. And then finally, the initial population. Well, that's when t equals 0. Initial, always think of t equals 0 when you see initial. And we can evaluate p when t equals 0. Go 5,000 over 1 plus 39 times e raised to the 0. So that's just 1. So that's 5,000 divided by 40. 5,000 divided by 40 is going to equal 125. Alrighty, so maybe a warm-up question or two, because 1b is also fairly straightforward. You don't really need a calculator for 1a, but for 1b I would definitely say let's pull out a calculator for this, because all we're really doing is we're evaluating 5,000 over 1 plus 39 e raised to the negative 0.2 times 10. And when you use a calculator, I did that in advance, I've got it over here, we're going to get approximately, where is it? 796.422, but since this is a population, perhaps it's best to round to the nearest whole number. 796 is the population when t equals 10. All right. Part C starts causing us to actually think about how this is related to a differential equation, because they're asking about the growth rate. In fact, it's asking for the time when the population growth rate is greatest. Now, we don't have to do a lot of hard work to figure out the time. We're not going to take any derivatives and set it equal to 0 or anything like that. All we're going to do is we're going to remember that the population growth is greatest when the population equals 1/2 the carrying capacity. That's one of the big concepts that we want to remember about the logistic functions. So since L is 5,000, we're asking the question, when is the population equal to half of 5,000? In other words, 2,500. So we'll set population equal to 2,500, and we'll see if we can solve for t. Oops. So 2,500 equals 5,000 over 1 plus 39e raised to the negative 0.2 t. So one thing we can do to solve, I didn't give myself much space here, did I? To solve for t is swap the location of the denominator and the 2,500. We get 1 plus 39e raised to the negative 0.2 t equals 5,000 over 2,500, which, because of the relationship that we started off with here, we already know that that's equal to 2. All right, so we'll subtract 1 from the 2. We'll divide by 39, right here. Divide by 39. Then we'll have e raised to stuff equals 1 over 39, so we'll take the natural log of both sides. Then we'll have negative 0.2 times t equals this, so we'll divide by negative 0.2. And that should be our t value. And if you need a decimal version of this, if you don't want the exact form, if you want a more realistic answer, then 18.381 is the t value that will yield 2,500. Of Of course, this is easy to check in a calculator. Just evaluate P of t when t equals that crazy number. And finally, the last question here would be express dp dt in terms of p. Again, we're not going to manually take any derivatives. We remember, I hope, that dp dt is equal to k times p times 1 minus p over L. And if we have that memorized, then all we need to do is substitute in the values of k and L that we already know. K we already discussed was 0.2, and L we already discussed was 5,000. And that's all we need to do. And we're done. So don't reinvent the wheel here. Don't redo derivatives that have already been done for you. Just use the formulas and go with it. All right. So I think we have time for another one on this video. So here's going in the other direction. In problem 1, we started with the population function, and we had to glean information to get the differential equation. Now we're starting with the differential equation, so we're probably going to go in the opposite direction. One thing to notice is that this does not look like some constant k times p times the expression 1 minus p over L. So that's going to be our first challenge. We want to make sure that our differential equation looks like that. So we have some constant times p times a separate thing. So we're going to have to factor some things out. And what do we have to factor? Well, we have to factor whatever it takes to make sure that there's a 1 here. Notice that the 1 is the only actual number here that's known. Everything else is expressed as a constant k, an unknown constant k, or an unknown constant L, or it's the variable p. So 1 is the only known thing here. So we have to make sure that that first term becomes a 1. So that tells us what we have to factor out. We have to factor 3p over 20 out. We don't have a choice. So dp dt is equal to 3p over 20 times 1 minus, and we have to figure out what's left here. So we're dividing out the 3p over 20, which means we're multiplying by the reciprocal of 3p over 20. So that means that the p in the denominator reduces one of the p's in the numerator. The 20 in the numerator reduces with the 1600 to get an 80 on the bottom, but that's going to be multiplied by a 3, and we're going to get 240. If you don't believe me, multiply it out and see if you end up getting back to where you started. Okay, that is the more standard form for the differential equation. So now we can see that the carrying capacity L is 240, and we can see that the value of K is that coefficient of P, which is 3 over 20. All right, great. Next step would be write an expression for P of T. We have all the information we need except for the B value. So that's why we are given the initial population of 20. If we start off with what we know, which is P of T equals 240 over 1 plus B times E raised to the negative K, which is negative 3 over 20, times T, we know that when we evaluate the initial population, in other words, when T equals 0, we know that we should get 20. So that means that 20 is equal to 240 over 1 plus B times, well, if we let T equal to 0, then this exponent becomes 0, so e to the 0 is equal to 1. All right, so 240 divided by something equals 20. Again, do that same switcheroo with the 20 in the denominator, and we can see that b plus 1 plus b, let's not swap the order, don't want to confuse anyone, is equal to 240 over 20, which is 12. So if 1 plus b equals 12, then b must equal 11. That's the only thing that was missing. So we have P of T equals that whole thing, but replace the b with 11. So 240 on the top, and 1 plus 11, e raised to the negative 3 over 20t is the denominator. So there's our population function. Notice that all we were given was the differential equation and the initial value, and using the formulas that we had memorized, we were able to get that p of t function. Once you get that equation, it's extremely straightforward to evaluate p of 20. You just evaluate this fraction when t equals 20. And when you multiply this fraction times 20, the 20s cancel out. So we can just type that into the calculator, and apparently we get 155. Again, it's a population, so I'll round to the nearest whole number and not worry about the 0.073. So what else do we have here? We have another question about finding the time. This time it says when the population will reach 50% of its carrying capacity. Okay. Notice that that's exactly the same question they asked before, even though they used different words. When I say they, I mean I wrote this question. So up here I said when the population growth rate is greatest, but that means when p equals 1/2 L. So this is really the same question, just with this new function. So that half of the carrying capacity is 120. So we'll set 120 equal to our fraction. And we'll go through the same algebraic process to solve for t. Again, we'll do that swapping of the denominator with the 120. So we'll get 1 plus 11e to the negative 3 over 20t is equal to, this is always going to be 2, right? Because we're taking our carrying capacity divided by half of our carrying capacity. So when we subtract 1, and then divide by the 11, and then take the natural log to get rid of the e, and then divide by the k value of negative 3 over, well, divided by negative k, which is negative 3 over 20. We're going to multiply by negative 20 over 3. That should be your t value. That's going to give us a p value of 120, and that is going to work out to be approximately 15.986.